Okay, everybody. Please sit down. I would like to start very quickly because we have only an hour today and we actually got a couple of nice talks and we have to make sure we keep ourselves in time. Welcome to the Maprg session. I'm Mirja Kühlemint, and unfortunately my co-chair Dave is not here today, but hopefully he will be back next time. We have an IETF session here, but we also have a Notewell, which is very similar to the IETF Notewell regarding property rights. So please, if you're not familiar with that, make yourself familiar with it. But I would also like to point out the code of conduct and any kind of privacy-related policies that we have in the IETF, which of course also apply to this meeting, and which is especially important when discussion get heated, right? Everybody should maybe think about a second to use the right words, to be friendly to each other, which I don't think it's a problem we usually have in this session, but it's still good to remind yourself about it. And then also another reminder that this is actually an IETF session here and not an IETF session. So while it's nicely integrated and we get like a nice exchange of people, and I hope everybody is enjoying this from like a research and an engineering point of view, the IETF working groups usually don't do standards, right? So that's an important difference. In Maprg, we mainly focus on getting researchers in here to present their measurement results. And I think this is very well received in the IETF as well. But like, be aware that this is not the same. Okay, that's the usual slides you will find in the slide deck if you need any of the pointers here. And this is a slide we already had the last time. So Dave and I would like to add another chair. Because as you can see, Dave is not here, so getting a little more coverage would be nice. But it's also a matter of outreach, right? So Dave and I do a lot of things where we try to contact people in the research community to get them here and present their work. So having more help with that will like extend our outreach and maybe also get different angles in. So ideally, we are looking for somebody who's like well established in the academic community and has contact there and is interested in engaging with people and bringing their work to the IETF or the IETF. We put up this call last time already and we got a couple of responses, and like we from our side were actually not very active about it. So we didn't make any decision yet. So you can still send us an email if you're interested to help out. And that's the point where we already get to our agenda. And there, if you have noticed or not, there was like a last-minute agenda update that I did this morning. So in the last couple of days, I actually reached out to a couple of people and just asking them for a deployment number for Quick, because that's a question I get very often, you know, how much Quick is out there at the moment. And I thought this is a nice group to actually, you know, collect these numbers and present them to you. So I have like 4 slides from 4 different companies giving me different kind of numbers, and I will present them to you. And you know, if you think this is something useful, then maybe that's also something that like we as the chairs could do more often in this group, not only for Quick, but maybe also for other protocols, just to get like an up-to-date number. Afterwards, we have a presentation by Nicholas about loss in SATCOM networks. And then we have 3 presentations of papers which have been presented just like 2 weeks ago, I believe, at the IMC conference. All really nice and good and exciting papers. One author is here in person, which is really great. And the other 2 authors will be joining us remotely. Okay. So because we have 4 talks in only 1 hour time, I will be very quickly here. So that's what I got in the last couple of days. I got a number from YouTube, which is kind of the number that we all might be aware of to some extent. So Quick had like within YouTube about 33% of the traffic was in December 2017 was Quick already, which was published in a SICOM paper and also presented in Maprg, I think. And the updated number is that they're now about 50% of the egress traffic volume. And this also aligns with about being 50% of the playout requests. I got this information from Ian, who I don't see at the moment, but like if you want more information, you can probably talk to him. Then I talked to Facebook, and they are rolling out Quick on between their own server and for their major applications. So for their major application, it's actually 80 to 90% of the traffic is using Quick. And that's Quick, IETF Quick version 23. And the other 10 to 20%, it's actually, some of them is fallback to TCP, of course, but some of them might be also connected to their rollout strategy. So like sometimes they decide to not use Quick, right? But like that, you know, is basically their rollout plan. Then I contacted Markus from Deutsche Telekom, who is actually here, and to get also the operator's view. So like if you look passively on your network, what's the number of Quick you see? So that's a number for any traffic that is UDP on port 443, which is assumed to be Quick. And what they see is about 10% in the fixed network here. 10% of the downlink traffic is Quick, and about 4% of the uplink traffic in terms of traffic volume is Quick. So he also presented a comparable number last year in TSVW, and you can see the number here. And actually, the percentage went a little bit down. So it used to be something 11 point something %, and now it's around 10. Which is a little bit surprising, but you can also talk to Markus about this. If you want to stand up so people see your face. Yeah, that's the guy. And then I got some numbers from Akamai, because they support Quick for their customers for certain products. So not all of their products get the possibility to use Quick, but most of the products that have actually large data volumes can use Quick, and can use Quick kind of by default, of course, if the other end supports Quick. So this is only possible for Chrome, because that's like kind of the only client that supports Quick. And it also depends a little bit on your geolocation. So basically they offer the possibility to use Quick the next time you connect to the same service to a large set of clients, but then that doesn't mean that like all of these clients come back to you and actually use Quick the next time they connect to you. So for example, in China, it's only about 20% of the clients that would actually use Quick, because a lot of the clients that claim to be Chrome are not. And so they don't even speak Quick. In terms of traffic volume, it's after all about like 1% of the total traffic volume. But that's also a lot, as you can see with the numbers here. Also interesting was that about 50% of the connections use zero RTT. So that's also well used and very interesting. Do you want to add anything, Igor? Or also raise your hand so people see you and can ask you questions. Actually, I have one more slide, right? So he was also so kind to not only provide a number, but also something over time. And this is a little tiny, so you can look up the slides in the proceedings. But this is kind of 2-minute samples about the amount of Quick traffic you can see. And split up by version. So they support different versions in line with basically what Google is deploying, right? Yeah. Okay. So that's just a very quick update that I squeezed in here, and I hope you find it useful. Thank you, everybody who provided the data, also on a very short notice. And if there are no questions, we just move on. Ian showed up. So Ian, that's the guy for YouTube if you have further questions. Yes. Okay. Then we go to the next presentation.
Hello, everyone. I know the timing is tight, so I will go quickly over the slides and be available for any questions. if you have. So this is conjoint work with lots of people. You have the names on the slides, and my name is Nicholas. We are focusing on losses. No, it's okay. Yeah, somehow. One of the thing is on satellite systems, the satellite link is actually loss-free. We don't have any losses usually, except for specific parts of India where you have very heavy rains and specific bands. However, we wonder whether we have losses somewhere when we use our accesses. And why? Because we usually use TCP proxies, not only for acceleration and these kind of things, but more for splitting the reliability management. So on the picture below, you have somehow a multi-gateway satellite system. So we see that there are many places where we could actually lose packets. But to have a better view on that, we just made a simple experiment. So we have a server in Isae, that's a school, with Pico Quick enabled. And so we have just been using a public satellite access and downloading quick packets. We have seen, so I have more data if you want to speak, and I don't have time to go through it, but we have done some Gilbert-Elliott modeling, and we ended up having almost 2% packet losses. So I had a chat with Gori earlier, and he told me that on his access, he don't have such losses. So that might be how the operator is tuning, doing some traffic shaping. That might be on the wireless links we have after the satellite terminal. So to have more ideas on where the losses come from, we have done another experiment using another type of satellite access. So this time we have been using Akamai servers. With their IETF quick implementation. We have used the loss identification methods on the draft proposed by Orange and Akamai. So one, we enter the router CNES. We are in our company network where there's very low losses, and the satellite here is the satellite we operate, so we have some bandwidth on it. So we knew we were alone on the satellite at this moment, on this part of the satellite. We're not that rich. And basically, we have 3 different points where we could make TCP dump measurements, captures. One is before the satellite gateway, one is just right after the satellite terminal, and one is just before the end user. Again, I don't have time to go through the details, but what the useful tool enabled us to do is to show that basically green is the end-to-end losses, and purple is the losses we have up to this point. So we know that from the point before the gateway, we know that before reaching the satellite gateway, we don't have losses. And then if we look at the purple part here, basically these are the losses we have that are happening at the gateway level of the satellite link. We have some tools knowing that it wasn't raining that day, so we know that the satellite was properly sized. There wasn't losses on that part. And then we have emulated 1% Wi-Fi losses, and we could see again the losses between satellite terminal and the end user. So to go back to our problem here is that losses can actually happen before satellite gateway, because we know some gateway manufacturers implement traffic shapers. So that is what we see here. And then another measurement we did is that was more some benchmark of my Wi-Fi access at home, and I could measure slightly less than 1% losses on on the wireless part. So that is something I use at my place, because satellite industry often focuses on physical layer problems. And when I explain to people that losing 1 packet out of 1,000 is a big problem for TCP, I just made these measurements using the same real satellite, where basically we have HTTP server and an end user. We don't have any proxies, and we just have these losses that are emulated after the satellite terminal. And we can see, just if we take 1 point, that if we lose 1 packet out of 1,000,000, the throughput is actually divided by 2. So the main point of my talk is that we do actually have losses on satellite links, satellite access, whether it is on the satellite part or on the ground segment or after the satellite terminal. If we are using Quick, that's a problem we will have to solve. So at the moment, we are looking at maybe to solve this issue. We know that for short files, Quick is actually great because we save the connection establishment time, so that is awesome. For short files, we do the same without proxies, and we want to achieve the same gain with Quick without proxies, but for large files as well. And for that, we need to do some tunings. So at the moment, we are thinking that one solution could be using coding in Quick, but then there are discussions on interactions between this congestion control in Quick and the coding we add. So for that, we have started a discussion document in a network coding research group on the interactions and best current practices on how we can actually neglect or not packets that have been recovered by a coding mechanism. So, and also to speak a bit more wider on all these topics that we have and issues we have in Quick with our high-BDP networks, we have a side meeting on Wednesday afternoon. So the room is open for anyone who wants to show results, discuss, and collaborate with us on this. So, thank you.
Yeah, thank you very much. I think we have a little bit time for questions if people want to ask something. Otherwise, it's also good to move on because of the time limits.
Thank you.
Okay, thank you very much. So our next speaker is Blake. Thank you for being here. And should be set up.
Perfect. Hey, thanks. So I'm going to talk about some work that we've done recently about combining endpoint and network data and what we can do with that. Just to level set TLS fingerprinting real quick, we have the client hello. We take some features like the protocol version, cipher suites, extensions, and we ideally want to map them to some responses of interest like the process name, the SHA-256, operating system version. So this is the idea, the kind of where we want to go with TLS fingerprinting, or what people typically want to do with TLS fingerprinting. We created a couple of open source tools that generally do network fingerprinting and some light analysis. They're both on GitHub. One of them is C, high speed. One of them is Python, where we do some experimental work. Okay, so this is kind of the key component of the IMC work, the network endpoint data fusion pipeline. It is currently getting data from 5 geographically distinct enterprise networks, so kind of scattered around the world, so we get a good representation of different applications. There are 24,000 users. It is I guess one of the biases primarily Mac OS and Windows. So these are instrumented managed endpoints. There's some Linux, but it's very small amount. And yeah, so basically we're monitoring those networks. We're collecting kind of typical NetFlow information, plus the fingerprinting information, so the TLS fingerprint there. And then the managed endpoints are also exporting NetFlow-like information through the AnyConnect NVM VPN agent. So that gives us, again, the network 5 tuple plus the SHA-256 hash of the process that created the connection, process name, and some operating system information. And we collect all of that data continuously, and then at the end of each day, we run a big data job that merges based on the 5 tuples and the timestamps. And then we end up with all of these kind of super flow records that have all of the network information that we need for fingerprinting, plus all of the ground truth that we can use for generating the labels. At that point, I guess at the I should say that we kind of piggybacked off the current security monitoring infrastructure. So they obviously need identifying information. For our uses, we don't need any of it, so we just strip it all to avoid some of those issues. And the last thing that I'll say about the data fusion pipeline is that throughout this talk, it will be very specific to TLS, but it is much more general than that. So it's actually applicable to pretty much any protocol. So as soon as we define a new fingerprint generation module in Mercury, the data fusion pipeline can automatically pick up on that and start generating daily fingerprint databases for that protocol. And then just kind of how we do that, I mean, it's pretty simple, right? So we get the fingerprint databases for each day, then we run a job to merge them so we get the master database. This is very simple, but kind of a really has a lot of nice advantages. So in terms of performing longitudinal measurement studies, like having the TLS sessions in the form of these like daily databases, it's very efficient to compute trends, right? So instead of looking at kind of terabytes of data, it's like a megabyte per day of data that we can look at. And in terms of the functional aspect of TLS fingerprinting, it allows us to age out older data. So data that we saw 2 years ago is probably not representative of TLS fingerprints that we would see today. And the actual fingerprint database is up on the GitHub as well. It's a slightly reduced database to avoid some issues, privacy issues. But it is updated. I try to update it every Monday, so I updated it right before the talk. And I think that should continue for the foreseeable future. And this is kind of the format of the database. So there's a lot of information. We represent the fingerprint as a string, a parenthesis string. We collect some metadata about the fingerprint, like when's the first time we've seen it, when's the last time we've seen it. We map all of the TLS parameters to the RFCs and report min and max implementation date. So we get kind of a sense of the age of the parameters in the fingerprint, some count information. And then something we do a little bit differently than previous TLS fingerprint databases, we give a list of all of the processes that we've seen associated with TLS fingerprint, which is probably a more realistic representation of what information a TLS fingerprint actually gives you. And for each fingerprint in the list, we give like the name, the SHA-256, and some destination information that we saw that process using that fingerprint string going to. And some quick database statistics. So we break up our fingerprints into 3 different sets. So passive is where we don't have any endpoint information. And so this is the majority of the sessions we see. We don't actually have endpoint information on all sessions, but we can still map those fingerprints to a list of destinations that they went to. The endpoint is the fuse data, so those fingerprints have the list of processes. The malware fingerprints, we basically recreate the data fusion process with the artifacts of a malware analysis sandbox. So we get the process attribution there. We have in total about 70,000 fingerprints from 46 billion sessions. This is growing. The rate at which it's growing is increasing as we deploy to more sites. So I actually haven't checked it in a couple of weeks. I think these numbers are significantly larger now. The last time I did check, we get about 2 billion new sessions per day, and 200 million of those are endpoint labeled. And this kind of ongoing continuous database generation is obviously really important because TLS fingerprints change. Just real quickly, this was very surprising to me, very interesting. So like, what does a fingerprint give you? If you go and look at presentations on TLS fingerprinting, it seems like this like magic silver bullet that's going to solve all your problems. In reality, it's a little trickier than that. So for a given fingerprint, we looked at the average number of processes that belong in each fingerprint and the average number of fingerprints that each process generates These are the mean and standard deviations of those. So it's kind of broken up into categories too. So Chrome and Firefox are browsers, email is like Outlook, etc. For the typical browser fingerprint, we see around 22 unique processes, and that's on the low end. And then for other fingerprints, they range from like 40 to 70 unique processes, and these are processes that are using the standard libraries of the operating system or OpenSSL. So there, especially for those categories, looking at, just observing a fingerprint string or a TLS client hello, you actually get very little information about what actual process generated it. So it's not this, magic bullet. There's some things you can do around incorporating the destination information that helps, but then you get into kind of like light machine learning. Okay, so some of the longitudinal studies that we were able to do with the daily fingerprint databases, this was actually, when I first saw this is what made me write the IMC paper, because it was really interesting to me. So we had been monitoring TLS 1.3 adoption for a couple of years, I think like everyone else. And, we expected that in August 2018, when the RFC was actually published, that we would see a huge uptick, right? That just kind of makes sense. At least to me, but actually, the months following the publication of the RFC, we actually saw a decrease in TLS 1.3 adoption, which seemed kind of counterintuitive. And then, 6 months after that or so, the support seemed to rise again. And, just looking at the, raw measurement numbers, it's kind of hard to explain why we saw these trends. But when you're looking at the kind of the ground truth that we know which applications are using TLS, both of those become obvious. So first, in terms of the increase that happened, March 2019 Mac OS, is there a clarification?
Can you go, George from APNIC, can you go back one, please? So that's a closed set, isn't it? That's all things seen that are TLS. What is the intertype ratio?
Yes.
So the variance in the set is not a reflection of increase or decrease in absolute sense. It's the variance in the set.
Yes, that is correct. And that's important. So, in March 2019, Mac OS released TLS 1.3 as the default system library, and we saw this huge uptick in all these different categories using TLS 1.3. Before that, pretty much the only two applications that used TLS 1.3 were Chrome and Firefox, or Chromium-based browsers and Firefox, and that was kind of it. So we understand the uptick. So the downtick was basically that first bullet point. Chrome and Firefox were the only ones using TLS 1.3 for a really long time. And this is kind of a breakdown of the percentage of applications that use TLS. So each of those are different categories. And what we see is that the overall percentage of applications that use TLS for browsers is actually decreasing over time. And I think this is a good thing. So most other application categories, most other applications, instead of just calling out to their home using HTTP, they're actually now using TLS, which is obviously good. The maybe not good thing is that they're typically using either standard OS libraries on Windows, which would result in TLS 1.2 connections, or they're using older versions of OpenSSL, which we see a lot. So, it's not that we see overall less TLS 1.3, we're just seeing a lot more TLS 1.2. The percentage of TLS 1.3 is actually increasing, or the number of sessions, raw sessions. So the last thing, real quick, I'm going to talk about some of the trends that we saw in malware with TLS fingerprinting. And I think, so TLS fingerprinting for malware identification has been a really popular subject. We looked into this, and straightforward TLS fingerprinting is maybe not the best solution to identify malware. So there's a kind of an open source list of JA3, it's a TLS fingerprint format, fingerprints, it's a hash. So to get it into our format, we kind of had to reverse engineer it, and we failed at some. So we were only able to identify 64 of the 67 that they listed at the time. And to their credit, they were very explicit about saying, you know, we haven't evaluated false positives, and there could be a lot of false positives from this list. So when we looked at their list, 55 of the fingerprints were heavily used by benign software. So if you were to use those as like a blacklist to identify malware, you would have an unreasonable number of false positives. The remaining 9 fingerprints, when we looked into the database, they were associated with older versions of Windows, like Windows XP, so they're really old, or older versions like 0.9 of OpenSSL. And those may or may not be good indications of malware, but yeah, they're better than the other 55 that definitely weren't. And so this last slide is looking at malware's abuse of censorship circumvention tools. So on the left, and again, the relative versus absolute numbers come into play here, looking at 3 popular tools: Tor, Ultrasurf, and Siphon. And so the absolute numbers of all of these tools increased dramatically over the past couple of years. It's just, you know, similar to TLS 1.3, malware is just using more TLS, so it kind of looks like it's going down. But consistently, we've seen malware use or abuse Tor. And then relatively recently, these other tools like Ultrasurf and Siphon, which obviously have very important uses, we've seen malware abuse those tools. And then randomization is another kind of general strategy to evade censorship. So I'm going to randomize my TLS parameters. We saw malware start doing this in June of 2018. The interesting thing, the most obvious, or the most common randomization strategy that they had was to randomize the cipher suites. So they don't touch anything else. They just take the cipher suites, add some, remove some, change the order. Again, they did it in a very naive way. So with their randomization strategy, they kept the same exact extension data and extension type. So that was completely static, and using the fingerprint format, we can hold, it's decomposable, so we can only look at the extensions or the cipher suites or the version. And so what we did was create a very simple rule where if I have seen this, extension, static extension data before, but I've never seen the cipher suites before, kind of log this fingerprint because it's interesting. And in doing that, we saw at the end about 9 different extension patterns that were very common in TLS fingerprints with randomized cipher suite strings, and they all map to the same variant of malware that's slipping my mind right now. We saw this over time, and there's different ones that were more popular, and all of the extension strings were kind of related to I think a specific version of OpenSSL. Yep, and that's it. So I really think that, I mean, for the measurement community, having this endpoint network data and a kind of a continuous way to generate these fingerprint databases is a really great way to do very efficient measurement studies over time. From the TLS fingerprinting point of view, having a database that isn't automatically updated provides very little value overall. And to actually make a TLS fingerprinting system, relying on things that are just available in the client hello, like the cipher suites and protocol version, is not really enough to give you a good solution. You can't really solve the use cases that people say that they're trying to solve. That's it.
Yeah. Thank you very much. We actually don't have time for questions, but we could still take 1 or 2 if you really want to. Okay. Thank you.
I'll be around.
Yeah. Talk to him. Okay. Go ahead.
Hey, that's a great analysis, Blake. Thanks. I had a couple of questions on the analysis. I have seen malwares typically lying SNI. right? So how is your prediction when malwares are lying about the SNI value?
But I'm sorry, I missed the.
Malwares, I've seen malwares typically lying about SNI in TLS, the server name indicator in TLS
Yeah.
that goes, they lie about that, right? They go to a malware domain, but they say they're going to Google, for example, right? So how does the prediction work in those cases?
So like through domain fronting.
Yeah.
So the actual TLS fingerprint string doesn't, it strips the connection specific information. So if the fingerprint is actually a good indicator for malware, then you could use that because it doesn't depend on the SNI. I think the general takeaway from our results is that TLS fingerprinting, without bringing in additional contextual information, is not a good way to identify malware.
Okay. And how would this work with, let's say, TLS 1.3 or DSNI, where SNI would get encrypted and then all that you get to see is client hello? Then would that be sufficient to identify the applications?
Potentially. I mean, TLS 1.3 adds a lot of parameters and the different applications use them slightly differently. So
yeah, but all the other parameters other than the client hello are encrypted, right? So how
what parameters are encrypted in the client hello?
Only the client hello is in clear text. The server hello and all the other handshake messages are encrypted.
So all of this work relies strictly on the client hello.
Okay. Oh, okay.
Yeah.
Okay, very quickly, please.
Just a quick question. Emmanuel Lochin is a superhero. So basically, you combine data collected from the network and data from end host, and you have a kind of engine. You put it inside, and you get a database from it, fingerprint database.
Yeah.
And this tool is available publicly?
So that tool is not available right now. It's a bunch of Python Spark jobs.
And the dataset, at least?
Yes, the dataset's on Cisco/Mercury and GitHub.
Okay, thanks. And congratulations.
Thank you.
Thank you. So now we switch over to DNS-related topic, and it will be a remote presentation. So I hope Kyle is there.
Yes, I am. Hi.
Perfect. Go ahead.
Great. Okay. Thank you. So this work is a collaboration between Rami Al-Baki and Michael Rabinovich at Case Western University, myself at Akamai. Can you go to the next slide, please? Okay. First, just a little background real quick, make sure we're all on the same page. ECS is one of the EDM options that you'll see in the pseudo record in the additional section of query responses. So the purpose of ECS is to allow authoritative name servers, ANS, to do their service, usually CDNs, based upon the client prefix as opposed to the recursive resolver or something else. So if you look at that little figure at the top, usually the topological information that ANS have is recursive resolvers IP address queries. What ECS gives you is an actual prefix of the client itself, the one that originated the query. So the ECS option in the query resolvers to ADNSs has a client IP address prefix and a source prefix. And the ADNSs use this to tailor the response, right? And then the ECS response
so you're fading in and out a little bit. So if you can make sure you're close to your microphone, that would be good.
Okay. I'll try to stay as close as possible. The DNS responses then from authoritative name servers to recursive resolvers have a scope prefix length set as well. And this is really a cache control. It tells the recursive resolver to what prefix length they should honor this cache record. So only clients covered by the client IP address to the scope prefix length should get the response. Next slide, please. So there's two high-level implications to ECS. One is a privacy implication, right? Authoritative name servers, and for that matter, anyone on the path between recursive resolvers and authoritative name servers, now have information about the client IP address, right? They didn't have that before. The RFC specifically recommends that recursive resolvers limit the prefix length to 24 bits in IPv4 and 56 bits in IPv6 to kind of reduce the impact of this privacy leakage. Also, because because authoritative name servers are not expected to universally need or support ECS, recursive resolvers are recommended that they probe for support in authoritative name servers and then only send the client prefix to authoritative name servers that are actually going to use it in order to reduce the potential privacy leakage. The other implication is a security one. And this is on the other side. This is on the CDN side. So the ECS option gives a relatively easy way to scan an entire CDN platform, right? From a single vantage point, you can just iterate through all of IP space, sending ECS prefixes, and get the entire network, the entire CDN's network, right? Some authoritative name servers and the CDNs that run them have implemented whitelists of recursive resolvers that they trust, and they only do ECS with those recursive resolvers. And this trust is via some out-of-band means. It's not actually part of the ECS protocol. Next slide, please. So these were the goals of our study then. We wanted to broadly look at the current behavior in recursive resolvers around ECS. Because of time restrictions, though, I'm only going to focus on the blue bullet points today. For the other things, I suggest you please go read the paper, as there's details on all of these topics. But today we're going to talk about adherence to the ECS scope and cache for recursive resolvers, and then several deployment pitfalls that we observed along the way in our studies. The data sets that we used for this are first logs from a major CDN's authoritative name servers, and in those logs we can see the IP addresses of recursive resolvers that send the ECS option to the authoritative name servers. We also conducted a series of internet-wide scans of all of IPv4 space. And in those scans, we sent DNS queries for a domain under our control to every single IP address. And what we find is either open recursive resolvers that send the ECS option on to our experimental authoritative name server, or far more likely, we find open forwarders that forward that DNS query onto a recursive resolver that then sends it to our experimental authoritative name server with the ECS option. I say that's far more likely because past research has actually observed that most open responding DNS IP addresses on the internet are actually some sort of home CPE device, like a home Wi-Fi router or something that then forwards the DNS queries on to a recursive resolver such as the ISP's recursive resolver. Next slide, please. So our first result then, and this is on honoring scope restriction on caching. We studied in the internet-wide scan the caching behavior of 278, or we attempted to study the caching behavior of 278 non-Google supporting ECS, non-Google ECS supporting recursive resolvers. Two things here. First, you'll notice the number 278 is pretty small. Deployment of ECS today appears to remain small based upon our data sets. Also, we excluded Google because the number of Google IP addresses that we found is actually, it's massive compared to 278. So it tends to skew our results, and we wanted to focus on just the non-Google IP addresses. Out of those 278, we were able to study the behavior of 202 of them using a variety of probing strategies. And the behavior we're studying here is their caching behavior. And the details of that are in the paper. But the high-level point that I want to share on this slide is what's in red there. Out of those 202 we studied, 102 of them actually didn't obey the scope caching restriction at all. What they're doing essentially is they're sending the ECS option in their queries, but they're ignoring the ECS option in their response, and they're not using it in their caching behavior at all. This is at best misleading to the authoritative name servers, because they get this information suggesting that they have greater control over the behavior of this recursive resolver than they actually do. Next slide, please. So we also observed in the internet-wide scans that some recursive resolvers, 33 in total, when they sent the ECS option, the prefix inside it was actually an unroutable IP address or IP prefix. In these cases, it was the loopback address. And this was a bit of a surprising observation to us. And we wanted to answer the question, could this be actually confusing to authoritative name servers? Could you go to the next slide, please? So to test this, we ran the following experiment. We sent 5 queries from our test machine in Cleveland, Ohio, to the authoritative name servers for youtube.com. Those 5 queries were all identical, except that they varied in the ECS option. In the first query, there was no ECS option at all. In the second query, we sent the ECS option, but the prefix was the test machine's own IP address truncated to 24 bits. And then in the final 3 cases, it was various forms of unroutable prefixes. In the first 2 cases, then we got servers that serve youtube.com in the location Chicago. Now you can see from the RTT that's actually pretty close. That's nearby to Cleveland, right? It gives a reasonable experience to the end user. However, when we sent unroutable ECS prefixes, we seemingly got mapped to servers world over. So obviously the experience is going to suffer, right? The RTT is higher and your content delivery will not be as effective. So clearly the answer to our question is yes, this can confuse some authoritative name servers. YouTube as one particular example here, right? Could you go to the next slide, please? Now, the RFC has language in it that says that authoritative name servers should at least treat unroutable addresses as equivalent to the recursive resolver's own identity. That wasn't happening here. One more slide, please. So we actually suggest that maybe this language should be strengthened. It should be changed from should to must, but also because obviously you can control your own behavior more than you control those you communicate with. We also think there might be a need for language on the other side of the communication as well. That recursive resolvers must send routable prefixes in the ECS option. And if that's not possible, then they should just not send the ECS prefix at all, or the ECS option at all. Next slide, please. Next topic was the impact of the source prefix length. So in the ECS option, you can send a prefix of any length you want, right? If it's IPv4, you can send from 0 bits all the way up to 32 bits if you so choose, right? And we set out to actually determine what the impact of varying that prefix length is on CDNs. To do this, we picked 2 different CDNs and then 800 random ripe atlas probes. We then resolved CDN accelerated host names for each of these CDNs with the probe's IP address truncated to various prefix lengths in the ECS option. Then from the ripe atlas probes themselves, we actually measured the TCP handshake RTT to those IP addresses that were returned by the CDNs. Next slide, please. So these are 2 cumulative distribution functions for the 2 CDNs, CDN1 and CDN2. As you can see with CDN1, if you send anything less than 24 bits, you get a longer RTT. So if you send less than 24 bits, your actual round trip time increases. With CDN2, on the other hand, you seem to be able to send all the way up to just 21 bits without your RTT actually increasing. So the answer of how few bits can you send without impacting performance for these 2 CDNs appears to differ, right? Next slide, please. On the upper bound on the number of bits you should send, the source prefix length, the RFC especially encourages, for privacy reasons, not to send more than 24 bits for IPv4, right? But we also just observed that for at least one CDN, and probably more, that sending less than 24 bits actually negatively impacts CDN performance. So it seems like there's the range of viable options is 24 bits, right? The alternative for recursive resolvers would be to keep some sort of state on a per CDN or per authoritative name server basis on how many bits they should send. And well, obviously that increases complexity, and that's really up to the recursive resolvers whether they actually want to implement that. But if in a general case, if you want to send the same number of bits to everyone, the answer is 24 bits. Next slide, please. Okay, this is our last topic then. And this is about hidden resolvers. So one more observation that we had from the internet-wide scan is that a number of the queries that arrived at our experimental authoritative name server carried prefixes in the ECS option that neither covered the recursive resolver's IP address or the forwarder's IP address. So they're from somewhere else, something else on the path in between the forwarder and the recursive resolver, right? But ultimately, the authoritative name server is going to use this ECS prefix to do its topological mapping to some edge server that will then serve content, right? So the question then really becomes, is this hidden resolver prefix an appropriate representative for the forwarder, the actual origin of this query, right? Next slide, please. You can break this down to 3 separate scenarios in our data set. And the first one is cases where ECS actually is hurting the mapping between the forwarder and some edge server. And those are cases where the hidden resolver prefix in the ECS option is farther from the forwarder than the recursive resolver. So you would have been better off actually not sending ECS in those cases. And that was almost 8% of the cases in our internet scan when you exclude one major public resolver that tends to skew the results. There's another case, though, where ECS doesn't actually help. It doesn't hurt, but it doesn't help. And those are scenarios where the prefix in the ECS option, the hidden resolver, is the same distance from the forwarder as the recursive resolver. So you went through the complexity of adding ECS, but you actually didn't gain any benefit from doing so. And that was another 20% of the cases in our test set. And then the rest are, of course, scenarios where ECS is actually helpful, and that's about 73% of the cases. So this result really highlights that merely supporting ECS alone does not guarantee that you're going to improve the end user experience, right? It's very important to look at the entire path from the edge device, whatever the user is sitting in front of, all the way to the authoritative name server, and make sure that the proper information is getting propagated throughout the entire path. Next slide, please. So I covered 4 topics here today, but there's many other observations. So I encourage you to please go check out the paper for any other points that you'd be interested in reading about. And I have time to take some questions, I think. Hopefully.
Yeah, thank you very much. We have actually no time to take questions, but like we will run a few minutes over anyway. So if you have a burning question, you can try now. Otherwise, I encourage you to read the paper and contact the author if you have further questions. Thank you very much.
Thanks.
So the next presentation is again remote, and as I just said, if people are okay with that, we will probably take a few minutes over. So we're running a little bit late. Sorry for that. Santiago, I think you can basically go ahead.
Hi, yeah. Are you guys able to hear me? Yeah, so today I'll be talking about characterizing JSON traffic patterns on the CDN. And this is joint work with Utkarsh and Moritz from Akamai, as well as my advisor, Professor Aruna. And yeah, you could go on to the next slide. So just to get right into this talk, we observed that JSON traffic is actually growing on Akamai CDN. So on the slide, we see a figure that shows the ratio of JSON requests to HTML requests over a period that started about 3 years ago. And interestingly, we see that JSON is actually 4 times more requested than HTML on Akamai CDN. And this has been something that's been growing over the observation period. It started at 1.5x, this ratio, and it towards the end, it ended up at 4x. And we observed this, and we decided to dig a little bit more deeper to figure out how JSON compares to other types of content. And we actually found that this trend is not just happening for HTML, it's also happening for other types of content. So JSON is actually the leading content type on Akamai CDN, except for video, depending on how you count video views and video hits. So next slide, please. So just as a brief background on what is JSON content. So JSON is just a text-based data format with key value pairs that's lightweight and structured. Next slide, please. So when we observed this, we asked why should we even look at JSON? What's important about this? And the truth is that little is known about JSON content delivery. There's a lot of work on looking at other types of content delivery on the web. So a lot of other works focus on optimizing for browsing and media content. And also a lot of work looks at security aspects of these different types of content. But when we looked at work that focuses specifically on JSON content, we didn't really find a lot of work on this specific content delivery. And And the question we had was, is JSON content delivery the same as other types of content, and do the same optimizations apply for this type of content? So we seek to answer these questions in this talk. Next slide, please. So what we do is we collect HTTP request logs from Akamai's edge servers. We use specifically this Akamai's CDN network as a vantage point to understand the global pattern of JSON traffic. And we collect two data sets. We specifically collect a short-term data set that spans 10 minutes of time, but it covers all of Akamai's edge servers. And we collect a longer data set which spans 24 hours of time, but it only covers 2 of Akamai's data centers. And we use the short-term data set to do network-wide coverage for overall characterization of JSON traffic. And we use the longer-term data set to do a wider temporal coverage just to analyze pattern characterizations. And just as a clarification, these data sets, every time a client makes a request to an Akamai edge server, HTTP request, then the server notes down information about the request, and this is the information we use in our data set. Next slide, please. So to understand our data better, we develop a taxonomy, and we specifically look at 3 main aspects of a request and response. And we specifically look at the source of the request. So we ask the question, where is the request coming from? We also look at the type of request and also the type of response. Next slide, please. So I guess in the interest of time, we'll specifically focus on 4 of these aspects. So for the source, we'll look at the device or the application that is generating this request. And we specifically use the user agent field in the HTTP request. And we use user agent databases and other things. More details are in the paper of what we do there to analyze the device and application. We also ask, does this request come from a human or is it machine generated? And when I speak about human versus machine generated, I mean, is this something that a human clicked the button or performed an action to generate a request? Or is there a machine that just, due to some program, is sending these requests? And this is pattern-based analysis that we'll go over later on in this talk. We also look at the type of request, whether it's an upload or a download request. And we look at the HTTP method for this. So if it's the GET method, then we consider this a download request. But if it's a post, put, or any other sort of method, then it's an upload request. And lastly, we look at the cacheability of the response of this JSON content using CDN cache labels. Next slide, please. So getting right into it, the first question we have is, what is the source of this JSON traffic? And we first look at the devices that generate or that request JSON content. So first, we find that the majority of JSON requests come from mobile and mobile smartphones and embedded devices. So we find that about 64% of content actually comes from these types of devices. And that's shown in the figure on the screen. So on the y-axis, we see different classes of devices. And on the x-axis, we see the percentage of requests that come from these classes of devices. And I'd like to also mention that there is a bar that, the blue bar, the dark blue bar, is unknown traffic. And it's unknown because it didn't contain a user agent in the HTTP request, or we just couldn't classify the user agent in our databases. We also see that 88% of this JSON is non-browser traffic. So it doesn't come from a browser. And this is interesting because there's a lot of research work on how to optimize browsing traffic, but we're unsure if this applies to this type of JSON content, to the majority of the JSON content. Next slide, please. So the second question we asked is, can we identify if it's a human or machine, with the idea that if it's a human sending this request, then the response is probably really sensitive in terms of human perceived performance. Versus if it's a machine, it may not be a sensitive response. It may just be data that's being varied back and forth between machines. So we use autocorrelation techniques, which are further described in the paper, to identify periodic JSON traffic. And we actually find that 6% of the JSON traffic we have is requested periodic. So these are clients that are periodically sending a request every X amount of seconds for the same JSON content. And on the figure on the screen, we have the percent, or we have a histogram of frequent periods or most requested periods per JSON object. And we see that there are spikes along standard periods. So there are spikes at the 30-second period, there's spikes at the minute period, the 2 and 3 minute period, and so on. And what I mean by standard periods is that they're not random. So they're not like there aren't spikes at 16 seconds or at 59 seconds or another off number. These are more or less pretty standard numbers. So using this insight that these that these objects are requested frequently, periodically, and they're also requested at standard periods, we identify this as machine-to-machine traffic, since it's very difficult for a human to very frequently make requests over prolonged periods of time, and to do so in standard periods as well. So when looking at this machine-to-machine traffic, we look at, we want to understand more what it's doing, and we find that almost 80% of it is upload traffic. So these are requests that are actually sending data to origin servers. And we also find that a large part of this traffic is uncacheable. So the caching optimizations that CDNs employ don't really help this type of traffic or don't help a large majority of this traffic. So instead, we suggest that perhaps this traffic can be deprioritized, since it's machine-to-machine traffic where a human is not awaiting a response. And we leave this deprioritization decision to be made up to network operators. Next slide, please. So then we asked the general question, does caching help all other traffic that is not machine-to-machine traffic? So we do find that almost 85% of requests are download requests, which makes them ideal for caching, since they're not sending data to servers, they're actually just receiving data. However, when we look at this traffic, we still find that a large number of these requests are uncacheable, so 55% are uncacheable. And we want to understand why. So digging a little deeper, we see that 50% of all of domains that do transmit JSON on the CDN actually don't use any caching at all for their JSON content. So not one of their requests are cacheable. So we create a heat map of domains. We specifically bucket domains into the domain industry that they're in, and this is seen on the y-axis and the heat map on the screen. And likewise, we plot the domain cacheability on the x-axis. Next slide, please. So interestingly, two very different types of patterns emerge for these domain industries. We have one set of domain industries that are almost completely uncacheable, so almost all of the domains are 0% cacheable. And we also have another set of domains that are almost completely cacheable, domain industries that are almost completely cacheable. And when we look at these domain industries that are uncacheable, we see things like financial services, business economy, and streams. So a lot of these industries do carry a lot of user personalized data, or for the streaming industries, they're more real-time data. So we would expect them to be uncacheable, since they do carry this user-sensitive data that we don't want to cache, or they carry this real-time data that's constantly changing. But likewise, on the other side, we see industries that carry more static content. So things like entertainment and news and media industries often just deliver content that doesn't change. So we asked, okay, since there's a lot of domain industries that don't benefit from caching optimizations, are there any other optimizations that can help? And next slide, please. So we look at ordering patterns. We ask the question, perhaps we can leverage information from ordering patterns between JSON requests. And we specifically look at JSON dependencies as an avenue for optimization. And what I mean by a dependency is, consider we have JSON object A, and then object B is requested next, and then object C is requested after that. And these objects are always requested in this type of order. We consider this to be a JSON dependency in HTTP requests. So the question we asked is, given a request for object A, are we able to predict that object B and C will be requested after object A? So we performed this analysis as well on clustered objects with similar URLs, and an example is shown on the slide. So if a URL has the same structure, but perhaps there's specific information within the URL that it's user specific or specific to the request, then we just cluster these types of URLs. And interestingly, so we use an n-gram model to analyze these request transitions, and we find that when considering the top 10 predictions, we do get about a 90% accuracy using these models. So we conclude that actually analyzing these ordering patterns would be helpful for optimization for things like prefetching or server push and so on. So yeah, in conclusion, we see that JSON is becoming a leading content type on the web. The majority is from mobile and non-browsing traffic. And we do present two avenues for optimization. So one is to deprioritize machine-to-machine traffic and to look at JSON ordering patterns. So with that, I'd like to thank you guys, and I'm not sure if there's time for questions.
Yes, Santiago, thank you very much for the presentation. We are already over time. So please just read the paper and contact the authors directly. Thank you for everybody who brought data, presented data, especially for the remote speakers, because it's not the most convenient time for them. It's late here as well, so thank you everybody for staying a little bit longer. I know this was a little bit squeezed, but we actually it was not easy to find any presentations, so I'm very happy that we got those remote presentations in finally to get a nice program. But next time we will have a longer session again, because we already have some stuff queued up. And therefore, thank you for today and see you next time.